Welcome to session 1 of electronic structure theory. In this session, what we're going to be talking about is we're going to go and apply the Schrodinger equation, which is the equation that governs the motion of microscopic, atomic, and molecular species. And we're going to apply this to all the electrons and all the nuclei of a hypothetical molecule, starting out from basically first principles. And when we do that, we run into the difficulty that we can never solve this, so we have to introduce various concepts. And one of the early concepts that we introduce in this session is what's called the Born-Oppenheimer approximation. And this is an approximation that has to do with the fact that electrons move much faster than nuclei. So this allows us to introduce some concepts, for example, the concept of an electronic potential energy surface. That's not something that really exists. It's something that we introduce as an approximation to solving this Schrodinger equation. We're also going to get equations for the vibration and rotation energy levels and wave functions of a molecule. We're going to introduce the concept of atomic units. This is just a shorthand notation that people use to describe the energies without introducing like masses and electron charges and the h bar, the Planck's constant divided by 2 pi. We're going to introduce the concept of molecular orbitals. And this, again, is something that really doesn't exist. It's something that we invented and we created as a device to approximately solve this Schrodinger equation. So we're going to introduce molecular orbitals. We're going to introduce the fact that the electrons are fermions, so they have certain permutational symmetry constraints on them. And this gives rise to something called Slater determinants. And we're going to talk for a little while toward the end of this session on what are the limitations that one faces when one tries to use the concept of orbitals and Slater determinants in describing chemical bonds and fragmenting the chemical bonds, because there's some difficulties that I think some of you have heard about that are called homolytic and heterolytic breakage of chemical bonds that one has to be careful about in using these approaches in treating the electronic structure. So that's the kind of thing that we'll be talking about in session 1. Okay, welcome to session 1 of electronic structure theory. I want to start out by trying to go back to the basics and say, how does one start to create things like the concept of orbitals and potential energy surfaces, and where do all those things come from? And I think the easiest way for me to explain this is, suppose that you were, Diane, you're from Mars. Maybe, no, I guess you should be from Venus. But you're from a different planet, and you've been endowed with knowledge of quantum mechanics, but you've never really heard about Hartree-Fock or molecular orbitals or energy surface and stuff. You come down to Earth, and I say to you, Diane, I think what we need to do is develop the theory of how we apply quantum mechanics to the motions of the nuclei and the electrons in atoms and molecules. And you say, that's a good idea. I want a PhD thesis, so I'll do that. So what you would do is, I think you would say, I know that in quantum mechanics there's this Schrodinger equation. And the Schrodinger equation, of course, appears in a time-dependent manner, h psi equals I h bar d psi dt. Or if the Hamiltonian happens not to depend on time explicitly, you can express things instead in terms of the time-independent Schrodinger equation, h psi equals E psi, where you get these E energy levels and these wave functions psi. Now, in principle, if we think of, we have this great big old molecule, maybe it's some polypeptide, it has lots of electrons and lots of nuclei. This psi would be a function of the positions of all of the electrons, and say there's n of them. So this would be a function of 3n little coordinates we call small r. They would describe the spatial coordinates of the n electrons. And psi would also be a function of the positions of all the nuclei in that polypeptide. And maybe there's m of them, which we would call, let's say, r1 through rm. And psi squared, really psi star psi, would give the probability density for finding the electrons at position R1, R2, R3 up to Rn, and the nuclei at positions capital R1 through capital Rm. So that's what, you say, I know quantum mechanics, that's what psi is supposed to do. I say, okay, good. But let's do it for the peptide. So the first thing you would do is to say, well, I know how to write, I first of all have to know how to write down what is the Hamiltonian, because I have to solve for these wave functions psi and these energy levels E. The first thing you have to do is write the doggone Hamiltonian down. I say, well, okay, let's do that. For this polypeptide, we have a bunch of electrons. And so we have each of those electrons has a kinetic energy, TE, the kinetic energy of the electrons. It's minus h bar squared over 2 times the mass of the electron, sum over j, 1 to n of del squared for electron j. That's the kinetic energy operator of each electron, additive. And one of the things I'd like you to pay attention to here are the functions that we see here additive functions of electrons and nuclei one at a time, or are they pairwise additive? Because that will affect some of the approximations that we have to make later. The first thing is to point out that the kinetic energy operator for all the electrons is one electron additive. That is, it's a term for electron 1 plus the same looking term for electron 2, the same looking term for electron 3, so forth. Then you say, well, H has more in it. It has the nuclei move also. So the nuclear kinetic energy is minus h bar squared over 2, sum over all the nuclei, j going 1 to m, 1 over the mass of the jth nucleus, del squared for the nucleus j. So this is the kinetic energy operator for the nuclei moving, all the nuclei. And they're moving in all three directions, x, y, and z. So those are the kinetic energy terms in the Hamiltonian for the electrons and nuclei moving. But then we have potential energy terms. And the main potential energy terms are Coulombic interactions among the electrons and nuclei. The terms that describe the electron nuclear Coulombic potentials are, now one thing I want you to notice about this is these are negative. That is, the electron nuclear Coulombic potentials are attractive because the electrons and nuclei are opposite in charge. So for example, this term is minus the summation over j going 1 to m, that's all the nuclei, times the charge of nucleus j, times the summation k going 1 to n, that's all the electrons, of e squared over distance of electron k to nucleus j. So they tend to be attractive potential energy terms. And then there are repulsive potential energy terms that are two in nature. The nuclei and nuclei repel one another. That's this next term. So that's plus the summation j less than k going 1 to m. So this is just a way we count pairs. So j less than k means nucleus 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. That's the way we don't double count interactions among nuclei. Charge of nucleus j, charge of nucleus k, e squared over distance between the pairs of nuclei. And then finally, there's another repulsive that is a positive potential term, electron-electron interaction, VEE, summation j less than k going 1 to n, because there's n electrons, e squared over rjk, distance of electron j from electron k. Now all those terms, electrons move, nuclei move, electrons and nuclei feel one another, electrons and electrons feel one another, and nuclei feel one another. They're always there. There can be other terms in the Hamiltonian. For example, if you apply an external electric field to the molecule or atom, if it were an atom, in our case it's some polypeptide that we're talking about, there would be terms, for example, that would involve the summation over all the electrons, 1 to n, charge of electron, position of electron k, dotted into strength of electric field, the so-called electric dipole terms. There are many other potentials you might consider adding, magnetic potentials and so forth. But for today's lecture, we're primarily going to just say, let's look at the basics, just all the terms that are always there, the kinetic and Coulombic potentials. Okay, now one thing I should mention too is, before we get any further here, is there's an important thing to understand about what is the zero of energy in our Schrodinger equation. See, these kinetic energy terms that we're talking about here, they turn out to be positive when we let them act on wave functions. There's some negative Coulombic potentials and positive Coulombic potentials. But I just want to say something right now about what does it mean to be zero potential, and what do these energies end up meaning relative to what? And what I'm trying to say here basically is, in the Schrodinger equation, the reference point of zero energy means all the particles, nuclei and electrons, separated from one another, they're all infinitely far from one another, and they're not moving. So for example, in these Coulombic potentials, they will all die if these distances among the particles are all infinite. So that's all the particles, if they're far away, the potentials will be zero, and if they're not moving, they'll have no kinetic energy. So in any atom or molecule, E equals 0 means that. So as a result, when one uses the Schrodinger equation with all these terms in the kinetic and potential energies to solve for the energies and wave functions of a real atom or molecule, the energies will end up being negative because these are stable species. That is, the polypeptide has a lower energy in its normal native state than it does with all the nuclei and all the electrons infinitely far away. So all these energies in our Schrodinger equation will end up being minus some huge number because they're all referenced to the zero of energy where the particles are far away and not moving. Okay, then I say to you, well, Diane, are you going to solve that Schrodinger equation for the polypeptide? It's a second-order differential equation in 3n plus 3m coordinates. And you say, whoa, I don't even know how to start solving such a second-order differential equation. So approximations have to be introduced. And the first approximation that people tend to introduce is the following. Diane says, well, I know that Schrodinger equation is too hard for me to solve, but I've heard some approximations that involve separation of time scales. And she says, even on my planet Mars or Venus, we take freshman chemistry, and we know that molecules' vibrations occur in a time scale of 10 to the minus 13 or 10 to the minus 14 seconds. And rotations of molecules occur in time scales of like 10 to the minus 11, 12, or 13 seconds. And I know that electrons move around in these atoms and molecules, I've heard at least, a lot faster than even 10 to the minus 14 seconds. They move faster than that. So she says to me, I know that in treatment of classical dynamical systems, sometimes people do what they call adiabatic approximations, where they say that the species that are moving sort of slowly, in this case it's the nuclear vibrations and rotations, maybe we can treat them on a different time scale than these rapidly moving electrons. And the way that we do this in most dynamical problems is we say, for the slow-moving degrees of freedom, let's pretend as if they actually weren't moving for a moment, and solve for the motion of the fast-moving objects, in our case it's the electrons, as if the nuclei, that is the slow-moving things, were actually frozen. Now, of course, we have to come back and patch up that approximation, but she says, well, maybe that's a way that we could make some progress here, like they do in classical dynamics. So what is normally done here in the Born-Oppenheimer approximation is that full Schrodinger equation. You say, let's go back to it for a moment, and let's just pretend that the nuclei weren't moving. So we say, let's suppose we had a Hamiltonian that contained TE, and the electron-nuclear attraction, electron-electron repulsion, and nuclear-nuclear repulsion, but suppose it had no kinetic energy for motion of the electrons, of the nuclei. Suppose, in other words, that the nuclei were not moving at all, but all the other terms were there. And we're going to call that Hamiltonian H0. It's the Hamiltonian that we say is the clamped nucleus Hamiltonian. So the nuclei aren't moving. It's not the right answer, but it's a first step in applying this adiabatic timescale separation that we have embodied in the so-called Born-Oppenheimer. So we say, let's just suppose that Diane could solve instead H0, the Hamiltonian without the nuclei moving, times psi k equals ek psi k. Now that H0 is a second-order differential operator in the 3n coordinates of the electrons, which I've represented here just by r, no longer r1, r2, up to rn, just little r. Because it contains these kinetic energy differential operators in those coordinates. It's no longer a second-order differential equation, that is H0 is no longer a second-order differential operator in the nuclear degrees of freedom because we've removed the nuclear kinetic energy operator from H to give H0. But H0 still depends upon where the nuclei sit because in the electron-nuclear attraction and in the nuclear-nuclear repulsion, the positions of the nuclei were still in there. So H0 is not an operator in the nuclear coordinate space, but it still depends, we say parametrically, it means it still depends on where the nuclei sit. So as a result, this Schrodinger equation here, H0 psi k equals ek psi k, officially its wave functions are functions of the electronic coordinates because this H0 is a differential operator in those coordinates, but the wave functions and therefore these ek energies still depend upon where the nuclei are sitting. That's why I still put in the wave function here capital R, and in the energy levels ek, I still put capital R because this equation would still depend upon where the nuclei sit. Anyway, this equation, H0 psi k equal ek psi k, that's called the electronic Schrodinger equation. It's the motion of the electrons feeling the nuclei, but with the nuclei held fixed at certain positions. What positions? Well, in a sense, you think of these as arbitrary positions that you define. You have to do this calculation over and over and over and over again at many values of these positions of the nuclei. Okay, now let's just progress a little bit, and then we'll come back and say how do we get from this approximation back to the real wave function. The idea is the following. This H0 is a Hermitian operator in terms of the electronic degrees of freedom. Therefore, its eigenfunctions, the psi k, form a complete orthonormal set of functions of these electronic coordinates, because the H0 is an operator in the electronic coordinates. So any function of the electronic coordinates, in particular our exact wave function that we want, these capital psi of r, little r, and capital R, can be written in principle as a summation of these electronic psi k's times coefficients. Now the way to think of this expansion is the following. Suppose you had a function of x and y, f of x and y. What I'm saying to you is that if I have a set of functions of x that are complete and orthonormal, I can write, and suppose I call those functions psi k of x. This is saying that I can take f of x and y is the summation over k of psi k of x, that's the complete set of functions of x, times coefficients, ck. But those ck's will have to carry the y dependence. That's why these coefficients chi k, which are the coefficients, I say still depend upon the capital R variables, because the capital psi wave function did depend upon these capital R variables. Anyway, I'm allowed to do this. I'm allowed to express this total wave function as a linear combination of these electronic wave functions times coefficients, with the coefficients still carrying nuclear position dependence. When I do this, when I take this wave function psi, and I go back to my full Schrodinger equation now, not H0, but H psi equals E psi. So what I basically do is I take this expansion for psi, summation of psi k chi k, go back to the equation that said H psi equals E psi, where H contained all the terms of H0, but also now contains the kinetic energy of the nuclei. What I do is I take that, H psi equals E psi, plug in for psi the expansion I just showed you, and then what I do is I multiply that through, multiply this Schrodinger equation through on the left-hand side by one particular psi L, star. So in other words, I take the Lth electronic wave function, psi L star, and I integrate over the positions of the electrons. So what I'm trying to do here is essentially to use the information I have in these psi's, the little psi k's and little psi l's, to get some equation for the coefficients chi. So let me just run through with you what I do there. And I just say that. So here's the H0, and also I've added in the kinetic energy operator for the nuclei, and I've pulled the minus E over to the left-hand side of the equation. So this is H minus E times psi, right here, summation of psi k chi k equals 0. That's the full Schrodinger equation. Take that equation, multiply through on the left by psi L star, and integrate over the positions of the electrons only. Now why am I doing the electron only integration? Because these psi k's and psi l's are eigenfunctions of H0, which is an operator in electronic coordinates. So psi k and psi l are orthonormal when I integrate psi L star, psi k, and I integrate over the electronic coordinates only, I get delta KL, because psi k and psi L came from a differential equation in the electronic degrees of freedom. That's why I do that. So when I do that, what I get is 0, that's the 0 on the right-hand side, equals a series of terms. Let me just lead you through where these terms come from. When the H0 acts on this psi k, I get EK psi k. Then when I multiply through by the psi L star and integrate, I get delta KL. So I pick out the term that's k equals L only. So that's where this EL of R times chi L of R comes from. Then another easy term is this term that says minus E up on the top becomes this term that's minus E chi L down here, because minus E times psi k chi k, when I multiply through by psi L star and integrate, I get delta KL again. So that's where this minus E chi L comes from. Then I also get terms that involve, now here's the hard things. I get 3 new kinds of terms. When these nuclear kinetic energy operator things here, this minus h bar squared over 2, summation over j equal 1 to m, 1 over mass of nucleus j, del squared for nucleus j's positions. Those del squared operators can act in 3 different ways. The second derivative could act on the chi k's and not on the psi k, or the second derivative could act on the psi k and not on the chi k, or I get a cross term, where there's the second derivative involves first derivative on the psi k and first derivative on the chi k. The term that involves the second derivative acting on the chi k, that gives this middle term here on this first line I'm pointing at right here. Because the psi L star integrated against psi k still gives me a delta KL, and then I get the second derivative stuff acting on the chi L. So in this first line of this equation, 0 equals, I've accounted for all 3 of those terms now. Now there's the other terms where these second derivative nuclear kinetic energy differential stuffs act on the psi k's. One of the terms involves, okay, now I get psi L is what I've integrated, I've multiplied through on the left. I get minus h bar squared over 2m, this differential equation, or differential operator acting on psi k, and then times chi k. That doesn't give delta KL anymore because it involves psi L on the left and the second derivative of psi k. It's called an off-diagonal second order because it's got del squared, what's called non-adiabatic coupling term, and I'll talk about that a little bit more in a minute. Then the other kind of cross term I get is when I get the second derivative can be written as first derivative times first derivative, and when I get the cross terms I get twice, and so here I get psi L, and then here I just get minus h bar squared over, not 2 because it's twice, that's where the 2 went away, mass of the nucleus j, del psi k dot del chi k. See, this is the cross term, first derivative of psi, first derivative of chi. These are also called non-adiabatic coupling terms. So these last 2 things here are called non-adiabatic couplings because they couple state k and state L. And these whole set of equations, which in principle are exact, they are called the coupled channel equations. Now, let me just lead you now through some approximations that we make here. So one approximation we say is, well, I wonder if we could ignore somehow these non-adiabatic coupling terms. And let me explain to you physically why it is that we sometimes get away pretty well with doing that. If you go back and say, these differential operators that are here, see that, for example, this term that's psi L, and then it involves this second order derivative with respect to position of nucleus J acting on psi K. Those matrix elements look very much like kinetic energy matrix elements for the electronic kinetic energy, but they're different. See, up there in H0, there was a term that involved, for example, psi L minus h bar squared over 2 times mass of electron, del squared for electron J, psi K. That was something that gave rise to the terms that are up here in this EL. But those terms are different because they involve 1 over mass of electron. This involves 1 over mass of each nucleus. And that should suggest to you that maybe these terms here are a lot smaller than some of the terms that were up here in this EL of R. Because 1 over mass of nucleus, a nucleus weighs like 1,867 or more times the mass of an electron. So the bottom line is that when people calculate these non-adiabatic coupling matrix elements, they do indeed find that they are small quantities compared to the energies, these EL of R's. So they make small contributions or effects on the total terms that are written down in all these matrix elements. So often, because the mass of the nuclei is much larger than the mass of the electrons, people say, oh, let's ignore these 2 non-adiabatic coupling terms. Now we'll come back and say when you can't ignore them in a minute. But just for a moment then, let's say, suppose you could ignore them. So this equation would then read 0 equals EL of R minus the kinetic energy operator for the nuclei moving minus E times chi L of R. You say, wait a minute, that looks like a little Schrodinger equation of its own. That essentially is a Schrodinger equation that involves the kinetic energy of the nuclei moving. That's the term in the middle. So this says nuclei move, and they move having this kinetic energy, and they move on a, now here's a word that comes in for the first time in these concepts, potential energy surface. That is, the concept of potential energy surface is these EL of R's. That just says, how does the energy of the nth electronic state vary with the position of the nuclei. And in the left-hand picture here, I've shown just a typical thing that you see, a blue ground electronic state, an excited electronic state. The blue state would be, for example, E0 of R, the ground state energy as a function of the position of the two nuclei in a diatomic molecule. The red curve would be E1 of R. Now, what were those E0 and E1s? They were solutions of the Born-Oppenheimer electronic Schrodinger equation. H0 times psi k equals Ek psi k. That H0 was our Hamiltonian without the electrons moving. So the way one actually gets these blue and red curves is you carry out a calculation at each position of the nucleus. You freeze the nuclei. You get the ground and excited and many, 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 many more excited electronic energy levels, and then you do that repeatedly as a function of these nuclear positions to generate the blue or red potential energy curves. So these potential energy surfaces are, because this Schrodinger equation I've written at the top here says the nuclei move with kinetic energy here, they have a potential energy that's the EL, and they have these energy levels that we label now E, and in a diatomic molecule we would label it L, which electronic state, J, M, and V, V being vibrational quantum number, J and M being rotational quantum numbers. And these chi's, these coefficients, would really be the vibration and rotation wave functions for the nth electronic state. So let me just say that one more time. Conceptually, H psi equals E psi. You introduce the Born-Oppenheimer approximation. That is what gives rise to these concepts of the EL of R's, these potential energy curves. Now, in a big polyatomic molecule, these ELs are not functions of just one internuclear distance. They're functions of all the internal degrees of freedom of the molecule. So they end up being potential surfaces, like I've tried to depict here on the right-hand side in a more fancy way. So Born-Oppenheimer approximation is what gave rise to the concept of potential energy, curves and surfaces. That then gives rise to the concept of vibration and rotation wave functions, V, J, and M. Each vibration rotation wave function belongs to a particular electronic state L. So for example, in this blue curve here, that L equals 0 electronic state has a V equals 0 and a V equal 1 and a V equal 2 and a dit. And also the V equals 0 level has J equals 0, J equal 1. So there's many, many horizontal black lines on this blue curve. They represent, in this approximation, the vibration and rotation energy levels of the blue ground electronic state. On the red curve, for L equals 1 that is, for that excited electronic surface, there also are many horizontal lines. The V equals 0, J equals 0, V equal 1, V equal 2. I don't draw many of these here, I just draw a few of them. So there's also a progression of vibration and rotation levels for the excited electronic state. But the thing I want to emphasize is these concepts of electronic state and vibrational wave functions and rotational wave functions are somewhat limited because they're derived from neglecting the non-adiabatic coupling terms, and they arise from our Born-Oppenheimer concept of treating how the electrons move fast compared to the nuclei moving slowly. Now, let me just bring you back for a moment to these coupled channel equations, because you said, well, Jack, you threw away these non-adiabatic coupling terms. When can't we throw them away? And the main case in which you can't throw them away would be if you had two electronic states, let's say K and L, that happen to have the EL of R and the EK of R. See, this set of equations here is valid for a certain value of L, but it's valid for all values of L. So if you had two electronic states that have potential energy surfaces, EK and EL, that come close or even intersect one another, that's when it turns out these off-diagonal non-adiabatic coupling matrix elements here cannot be neglected. And in that case, you actually have to think of solving the top equation for, let's say, EK of R, and also for EL of R, the two separate electronic surfaces, and then you treat these last two terms, these coupling matrix elements, as perturbations that sort of mix or couple or connect the two states. So for example, in this right-hand picture that I've shown here, we have a typical picture of some organic molecule here, some diradical, that's undergoing a process where, for example, in this excited state here that I've drawn, and I've tried to sort of show you some excited state that varies as a function of some angle. It sort of has this parabolic shape that I'm pointing at here, being intersected by another state that is this other sheet of this purple surface here. Right near where those two sheets intersect one another, what I'm saying is that you can no longer describe the total wave function as being just dominated by one psi L times chi L. In other words, it's not just a psi that would describe this electronic surface times a chi that would describe the vibration rotation. Right near these couplings, there would be two dominant terms. The psi that corresponds to this one potential surface and the psi that describes this other potential surface, and their chi's get all mixed together. So that's when these non-adiabatic coupling terms are important to consider. Near these surface intersections, they're sometimes called conical intersections, or seams on potential surfaces. So in these cases, you talk about processes where a system might go onto one surface and then undergo a crossing onto the other surface. That's the kind of thing that these non-adiabatic couplings are important for. Okay, so let's come back now to, we have Diane came from Venus or Mars, and she had her Schrodinger equation. She said, well, I know about adiabatic stuff. That gave rise to Born-Oppenheimer. Let the nuclei move slowly and solve for the motion of the electrons as the nuclei are at various positions, and then use those energy surfaces to subsequently solve for the motion of the nuclei on those separate surfaces. But I still go back to Diane. I say, okay, Diane, even if the nuclei are fixed or held constant, we're doing Born-Oppenheimer, we hold the nuclei at some distance, how are we going to solve for these electrons moving around? And she says, well, you solve H0 psi k equals Ek psi k. And I say to her, well, how are you going to do that? Because, see, H0 still is a pretty tough operator. It involved a sum of kinetic energies for all the electrons. She says, well, it's additive, so maybe separation of variables will be useful to me, Jack. Okay, wait a minute. It also involved a sum over all the electrons of each electron feeling all the nuclei. She says, oh, that's also additive, Jack. Electron by electron by electron. Separation of variables might help me. And then she says, well, it involved the nuclei and nuclei repelling one another, but that doesn't even depend on the electrons, okay, so that's not a problem. But then she says, but Jack, there's this last term, the pairwise interactions among the electrons, this VEE. It's not pairwise additive. 1 over R12 plus 1 over R13 plus 1 over R14, 1 over R23, 1 over R24, 1 over R34. Uh-oh, it's functions of electron pairs of coordinates, not additive. So because of that, her differential equation, H0 psi k equals Ek psi k, is not having in its H0 a sum of terms that are the same for each electron, one after another, after another, after another. So she can't apply separation of variables theory. So what does she do? Well, she says, well, maybe I could cross my fingers and ignore that for a little while and maybe pretend that down the pike we could approximate this VEE by some other potential that is pairwise additive. Now this is where we're going to what we call Hartree-Fock theory, or by introducing what we call a mean field approximation. Mean sort of meaning average field approximation. And what we're doing here is we're saying we know this VEE is going to kill us. We can't solve the differential equation. But let's try to take some steps that say in a little while we're going to introduce an approximation to VEE that is pairwise additive. I mean, that is additive, one electron at a time. It's not pairwise additive like this. Once we introduce that approximation, then we'll have to say, well, that was just an approximation, so we have to have some systematic mechanism, perturbation theory, for example, or variational approximations, to go back and say, okay, once we've introduced that approximation, how do we go back to this full VEE? That is, we have to take VEE true minus the approximation as some perturbation and introduce a framework where we can introduce improvements upon that approximation. Okay, so the point right here is just for a moment, let's pretend that VEE wasn't pairwise additive, but somehow was just additive, one electron by another, by another, by another. If it were, then we know that the wave function that we're after could be written as a product of some functions for electron 1 times function for electron 2 times function for electron 3 times function for electron 4 times function for electron 5, because all the terms in H0 would be one electron additive, one electron by another by another. Now, of course, VE is not one electron additive, so the true size cannot really be written exactly in terms of products of these things, which we're going to call orbitals, or actually spin orbitals in principle. So here's where the word orbital first arises. It arises when one says that as you go down your hierarchy of approximations, once you introduce an approximation to the pairwise additive VEE that's going to be one electron additive, that allows you to think of your wave functions as being products of functions for each electron. We call those functions orbitals, or actually those functions times alpha or beta we call spin orbitals. So for example, when we talk about a carbon atom, a 1s alpha, 1s beta, 2s alpha, 2s beta, 2p m equal 1 alpha, I guess that would not be a carbon atom, would it? It would be a boron atom. This is a chemistry class, so I should know that. That particular boron atom and that particular electronic configuration, as we call it, the whole idea of those orbitals and that way of talking about the particular electron occupancy of those orbitals, that's predicated on this replacing the pairwise additive VEE by some approximation. So I just wanted to mention the VEE is not additive, it's pairwise additive, and that's going to make our concept of these orbitals or spin orbitals an approximation that we have to justify and improve upon. But there's more that Diane will have trouble with when she tries to solve H0 psi k equals EK psi k. The psi k, the H0 operator, if you reflect back on it, it has minus h bar squared over 2 times the mass of the electron, del squared for each electron. Now that del squared, if you reflect back on your undergraduate PChem class, you say, what did del squared have? Well, it had a bunch of angular derivatives, but its radial derivatives were 1 over r squared d by dr of r squared d by dr, acting on psi. And if you write out that term, it would have the 1 over r squared d by dr of r squared d by dr. The first derivative with respect to r acting on the r squared would give a 2 times r. So the minus 1 over r squared times 2 times r would give minus 1 over r d by dr. So here I've got minus h bar squared over m, because the 2 canceled, 1 over r d by dr. Now that term there, I want you just to listen to that one for a moment. Minus h bar squared over 2m, 1 over r d by dr. That term varies as 1 over r. There's another term in the Hamiltonian that arises from the nuclear attractions, minus z e squared over distance of electron to nucleus. That term also varies as 1 over r. Those two terms there are terms that are the two that have a 1 over r dependence on them. The part of the kinetic energy of the electron moving and the electron nuclear attraction. Now those terms, when they act on psi, they're going to give trouble. They're going to give divergence or blowing up or ill-behaved behavior as r goes to 0. That is the distance of the electron to nucleus k. As that goes to 0, this term is going to give trouble unless it just turns out that the wave function has a behavior that the first term and the second term cancel. We'll talk about that just for a moment here in this next to last thing. So what I'm trying to say is that proper wave functions that do not blow up, because wave functions are normalizable objects that have to do with probability amplitude for finding the electron somewhere, and that can't be infinity. It has to be integrable to give 1. So anyway, the fact that this first term can't blow up leads to what we call a cusp condition. And we write this first term at the bottom here as d by dr of psi must equal minus m, the mass of that electron, times z e squared over h bar squared times psi. Those two terms must cancel as the electron comes close to the nucleus. So what does that mean? That means the slope of the wave function, that's what it means, d psi dr, must be negative minus m z e squared over h bar squared. They're all positive. So minus m, minus all this junk here is a negative quantity times psi. So the slope must be minus psi. So that means that if psi is positive, then its slope near a nucleus, let me go to the next transparency here for a moment. Near a nucleus, say the wave function is positive here, then its slope must be non-zero and negative. That's what that means, this cusp condition. There's also another kind of cusp condition. If you look at the terms that involve the electron and electron interaction, the E squared over distance between electron K and electron L, there's also a term in the kinetic energy that can be written as the relative motion of the two electrons relative to one another that has a term again that's 1 over RKL, just like this electron nuclear term. And that gives rise to another kind of cusp condition that's called the electron-electron cusp condition. See, the thing we just talked about in more detail was the electron nucleus cusp condition. There's also the electron-electron cusp condition. In its term, its factor basically says that the slope of the wave function as the two electrons approach one another, K and L, must be positive and have this 1/2 m electron E squared over h bar squared. So that what we're saying here basically is that near a nucleus, the wave functions that are acceptable must have non-zero slope. See, the wave function dr near the nucleus must be non-zero and must be positive. So the wave functions have to have this non-zero cusp near the nucleus. And the wave functions have to have a non-zero and negative slope. So they have to have the form where positive slope here. The wave function has to have this character as the two electrons come close to one another. They have this cusp type behavior here. And you say, who the hell cares about this? Well, the problem is that when we start to do electronic structure theory calculations, the kinds of wave functions that we use in our finite computers and finite intellectual strength that we have, approximations, if they don't have these cusp behaviors in these trial wave functions that we try to cook up, they violate these fundamental premises that the wave functions have to have. And I just want to point out to you that when we do calculations, electronic Schrodinger equation calculations, using radial, what are called Slater type orbitals that we'll talk about later, that have a distance dependence relative to the nucleus K of e to the minus zeta RK, that is, Slater orbitals have that functional form, so they fall off as e to the minus zeta RK, with RK meaning the distance of the electron to nucleus K. A function like that, you see, does have the right cusp behavior, because if I take the derivative with respect to r of that function, I pull down a minus zeta times e to the minus zeta RK. I let RK go to 0, so that gives the slope is minus zeta. It does indeed have this behavior of a negative non-zero slope at the nucleus. You say, oh, that's good. Well, the problem is the most common basis functions that we use in our calculations are Gaussian functions, like e to the minus alpha RK squared. In Gaussians, we call these exponents alpha. In Slaters, we tend to use zeta. This function, if I differentiate with respect to RK, I pull down a minus alpha times 2 RK. So I get minus 2 alpha RK, e to the minus alpha RK squared. I let RK go to 0, and I get slope equals 0. So Gaussian functions do not and cannot have this non-zero negative slope near nuclei. So that's a problem. Now, it turns out that these cusp conditions near nuclei are going to plague calculations that involve any kind of physical property where you're talking about electron density near a nucleus. Like in NMR, you often are talking about the unpaired electron density near some nucleus that might give rise to hyperfine splitting. So in those cases, Gaussian basis functions are difficult things to actually use because they give this problem that they can't give the right cusp near the nucleus. Also, as you'll see pretty soon in these series of lectures, most of the time the trial wave functions that we use in our electronic structure calculations don't even have in them the capability of having an electron-electron cusp. That is, they have no ability at all to actually describe this kind of cusp behavior as two electrons come close to one another. They try to describe it in terms of sort of a soft, instead of a sharp cusp, a soft avoidance in the wave function as the electrons come close to one another, but with a zero slope in there instead of this proper cusp behavior. So these are important things to keep in mind because they actually limit the accuracy of the current methodologies. Okay, so what have we been saying so far? Diane solving H0 psi k equals EK psi k. H0 has a separable, that is a pairwise additive electron-electron interaction she's going to have to deal with. The wave functions also have these nuclear and electron cusps that she might have to deal with if she wants to do really high-level calculations. Okay, now those are her problems that for the series of lectures from now on we're going to have to face up to, non-separability and cusps. But for the rest of this lecture, what I want to do is to talk about two more things, and then we'll end this lecture. One is I want to make a small digression to just explain what are called atomic units. And then secondly, I want to come back and talk about this idea of orbitals and taking a wave function at least approximately to be a product of orbitals, 1s alpha, 1s beta, so forth. So atomic units. Why do I talk about this? Because most electronic structure programs that we use actually spit out the energies that they compute in these kind of units, and I just want you to know what they are. And the basic idea is the following. Suppose that I said to you, everywhere in the Schrodinger equation, I want you to take the position of the electron and set it equal to a quantity A0, which will have units of length, times a dimensionless quantity, say Rj prime. So I'm just saying express every coordinate, every distance in that Schrodinger equation in terms of a dimensional thing that we're going to call A0, it'll have units of length, times a dimensionless amount that we'll call, say, the prime variables. When we do that and plug the expression here, R equals A0 times R prime, into the Schrodinger equation, where we used to have minus the kinetic energy of the electrons is minus h bar squared over 2m del squared, we will now have minus h bar squared over 2m del squared times 1 over a0 squared. These dels will now refer to different derivatives with respect to these primed coordinates. So the 1 over a0 squared arises just because in the kinetic energy there was a second derivative, and that's where the 1 over a0 squared came from. In the electron nuclear attraction potential, we'll just have minus the charges of the nuclei, E squared, divided times 1 over Rj prime, and 1 over a0. That's just because Rj prime times a0 was the original Rj. And then in the electron-electron repulsion, of course, we'll have 1 over Rjk primed and a 1 over a0. So when we put these pieces together, the kinetic energy will have terms that look like everything's familiar except 1 over a0 prime. The electron nuclear and electron-electron repulsion terms will have 1 over a0. And you say, well, that means they're going to scale differently with this 1 over a0, Jack, so what are we doing here? Well, the basic idea is the following, that if we say that a0 has units of length, then, for example, in the electron-electron and electron-nuclear repulsion terms, E squared over a0, E squared over a0 appears in there. And that has units of energy, charge over distance. That's Coulomb energy. So what we want to do is take the VEE and VEN and right away just pull out of them an E squared over a0 and factor that out. So we take the total Schrodinger equation, H0, which is kinetic plus VEE plus VEN, and factor out an E squared over a0. It factors nicely out of the V's, that's not a problem, because it was already obvious in them, E squared over a0. But in the kinetic energy, there's no E squared, and there's two a0s. So what we end up with in the kinetic energy is an E squared over a0 that we factor out, but then we end up with this screwy h bar squared over 2m, 1 over an extra a0, and 1 over an E squared that we had to put in there to cancel out the E squared we factored out. So we made the kinetic energy uglier. Unless we just happen to choose a0 equal to such that we cancel out all these terms in the kinetic energy. See, if I choose a0 to be h squared over mass of electron and E squared, then all this junk that's in front of the kinetic energy del squared will end up just being a half. So by making that choice, a0 is h bar squared over E squared m, which happens to be, if you plug in values for these quantities, 0.529 angstrom. It's called 1 Bohr. That's where the atomic unit of length called Bohr comes from. When you do that, then the kinetic energy operator just has minus a half del squared. All the h bars and m's and e's are gone. The potential energy has minus z over r and 1 over rij. So the bottom line is the Hamiltonian can be written in terms of E squared over a0 times factors that involve kinetic energies with no m's and no h bars and nothing like that, just minus a half del squareds, and kinetic and potentials that just have terms like minus z over r and 1 over rij, and that e squared over e squared over a0 that you factored out. If you choose a0 to be this one Bohr thing, then e squared over a0 ends up being 27.21 EVs, and it's what we call 1 Hartree, or 1 atomic unit of energy. So the bottom line is that in programs that are in routine use these days, the Schrodinger equation is written in terms of like minus a half del squared for kinetic energy, minus z over r for electron-nuclear attraction, plus 1 over rij for electron-electron repulsion, no e's, no m's, no h bars, because it spits out energies in Hartrees and it uses lengths in Bohrs, and those are called atomic units. Okay, so let's come back now to Diane's first problem that she has in solving H0 psi k equals Ek psi k. The problem was that the VEE was not pairwise additive. But what if somebody could cook up an approximation to VEE that we're going to call a mean field, that's what this MF means, approximation, that would look like the summation over all of the electrons, j equals 1 to n of V mean field of Rj. That is, it's V of electron 1 plus V of electron 2 plus V of electron 3, not having any terms of like electron 1 and 2 or 2 and 3. It doesn't have that in there at all. If that were the case, then her H0 would have a kinetic energy that's additive, electron 1 plus 2 plus 3 plus 4. It would have electron nuclear attraction that's additive, electron 1 plus 2 plus 3 plus 4. It would have electron-electron repulsion that is additive, 1 plus 2 plus 3 plus 4, if you could not have VEE, but if you could have this thing instead. In that case, then she would say, oh, I took differential equations, and I know whenever we have an operator that has all the terms of particle 1 plus identical looking terms for 2 plus 3 plus 4, what we can do is we can say the wave function that would be psi k would be written as a solution of this first term acting on some phi times a solution of the second term acting on another phi. So we can write our wave function as a product of these phi's for electron 1, a different phi for electron 2, a different one for electron 3. Then I say, well, Diane, you forgot about something. Electrons are fermions. Those Hamiltonians they commute with permutations of electron 1 and 2's names. So the wave functions have to be either even or odd under these permutations. She says to me, that's okay. Because what I can do is I can take these products of spin orbitals 1 times 2 times 3 times 4 times 5, and I can make them into what we call a Slater determinant. And the way this works is, that is, I can apply what's called the antisymmetrization operator to this product of spin orbitals, 1 over n factorial to the minus a half, number of electrons factorial to the minus a half, the summation over all permutations of these electrons' coordinates of a sign factor times a permutation acting on this. This is the kind of thing that you learned in undergraduate or first-year graduate quantum mechanics, that the wave functions, for example, phi 1 of electron 1, phi 2 of electron 2, when we put these vertical lines around it, we really mean this so-called Slater determinant. 1 over the square root of 2 factorial, that's 1 over square root of 2, phi 1 of electron 1, phi 2 of electron 2, minus phi 2 of electron 1, phi 1 of electron 2. See, that's just the minus, that's the sign factor, times the permutation of those two spin orbitals. So she says, okay, I can have Slater determinants. Okay, so what do we got so far now? Before we actually go on to how do we actually get a good mean field approximation, this VMF, because so far we're just saying if she had one, what we could do, we could introduce spin orbitals and we could make Slater determinants out of them. I need to practice with you a little bit about the properties of Slater determinants, because here's the big problem here. This whole concept that we can have orbitals and we can make Slater determinants, as we go further in the series of lectures, you'll see, oh, that's the starting point of most of the approximations that we use. Let's select a Slater determinant for that boron atom that's 1s alpha, 1s beta, 2s alpha, 2s beta, 2p m equal 1 alpha. Let's take that product of orbitals and make a determinant out of it, and we say that's a decent approximation to starting, and that's something we'll start with, and then what can we do? Well, the problem is that sometimes even that assumption that you can write down a single Slater determinant like that describes your atom or your molecule might be totally bogus. And I want to now display to you some problems that arise with the assumption that you might be able to write down such a wave function. And so to do this, let me just try to talk about a simple model system, but you'll see it's applicable to a wide range of problems. Suppose you had an olefin, and suppose we just focus on the last two electrons in that olefin that occupy the pi orbitals. So we have, let's say, ethylene. We're not even going to talk about the carbon 1s squared or the carbon 1s squared or the CH bonds and the CH bonds and all that. They're in our big Slater determinant. That ethylene would have 6 for carbon, that's 12, 13, 14, 16 electrons in it. It would be a 16 by 16 Slater determinant. But the last two rows of that Slater determinant would involve, for example, pi alpha, pi beta, the two electrons that occupy the carbon-carbon pi bond. So let's just talk about two electrons in those pi orbitals. And it turns out that the analysis I have here doesn't depend upon the fact that there's 14 more of these electrons in these other orbitals. That is, it's rigorous, but I'm going to mainly just focus on these two electrons. Okay, what I want to try to do with you now is to pretend that you have this olefin, and you would like to try to describe a physical process where you take that olefin with its pi orbitals, here, and here's the pi bond, and I'm going to take that molecule and I'm going to twist it. So I'm going to take it in its framework and I want to twist it and form a Born-Oppenheimer energy surface as a function of this twist angle to break the olefin into a radical here with an electron in this p orbital and an electron in that p orbital. Let's see how this goes. Well, Diane, I say to you, we have this olefin and there's 2 electrons in this bonding pi orbital. Could we write a Slater determinant for that? Well, she says, yeah, Jack, a Slater determinant would be pi alpha for electron 1, pi beta for electron 2. And that 2 by 2 Slater determinant, if I think about it or write it out, I could write it out in terms of 1 over square root of 2, 1 over n factorial, pi alpha for electron 1, pi beta for electron 2, minus pi beta for electron 1, pi alpha for electron 2. So there's the 2 terms. And you would say that Michael Morse taught me this. This singlet function has a symmetric spatial function. See pi alpha and pi beta. It's symmetric for the spatial part, and then it's odd, it's antisymmetric, alpha beta minus beta alpha for the spin part. Good. How about if we talked about, instead of putting 2 electrons in this pi orbital, there's also the pi star orbital. Let's talk about putting 2 electrons in it. And Diane says, I can do that too. Pi star alpha, pi star beta. That's the determinant. If I write it out, it would be pi star electron 1, pi star electron 2, symmetric spatial part, alpha beta minus beta alpha. That's what makes it a singlet. Great. Now we get a little bit harder though. I say, what about, she says, why are you making me do all this stuff, Jack? Because I want to show you that when we do this calculation of taking this molecule that you might think has 2 electrons in the pi orbital, pi squared in other words, and break it apart into the diradical, this pi squared function that you write down there will have some problems. And we will have to mix in some of these other functions to correct the problems. So I want you to practice going through these other functions. So I say, let's consider a situation with 1 electron here and 1 electron here. Pi 1, pi star 1. And let's do a triplet state. She says, okay, good, I can do that. Pi alpha, pi star alpha. That's the ms equals 1 component of the triplet. That's right. It involves, see, when I write that guy out, I would get pi alpha for electron 1, pi star alpha for electron 2, minus pi alpha for electron 2, pi star alpha for electron 1. Sorry, I had to pause there for a moment. So I get an odd spatial part times an even spin part, alpha alpha. There's also a beta beta. So Diane says, well, I could do pi beta, pi star beta. Yeah, you could do that. That would be the next one I've written here. But then we come to the 2 toughest terms that because she says, is that all, Jack? Can I go home now and get my PhD thesis? Nope. Remember, triplet states also, they have ms equal 1. You've written that down. Ms equal minus 1. You've written that down. But the ms equals 0 triplet, she says, I forgot how to get that. Well, the way you get it is you go back here to this red pi alpha, pi star alpha, and you apply the lowering operator. the S minus lowering operator. And that gives this bottom red term here, which would be pi alpha, pi star beta, see that lowered electron 2 spin, plus pi beta, pi star alpha. So you take this alpha alpha guy and you apply the lowering operator, which gives a beta alpha plus a alpha beta. And that's what gave rise to this pi alpha, pi star beta, plus pi beta, pi star alpha. So this particular triplet state, the ms equals 0, has two Slater determinants there. So one thing I want you to watch is that your ground state singlet, pi squared, your pi star squared, excited singlet, and your ms equal 1 and ms equal minus 1 triplets, they could be expressed in terms of a single determinant, single Slater determinant. But if I said to you, I would like to do a calculation on the triplet pi star state of an olefin that has ms equals 0, I could not use any single determinant to do so. It would involve these two single determinants. You couldn't do it assuming a single product wave function. So even Diane's additive mean field approximation, introducing the concept of orbitals, would not allow me to use, though, a single Slater determinant. I would have to use a combination of two Slater determinants, these two. Then finally, I don't want to go too much longer into this because I understand it's painful. I say to you, Diane, we forgot about the singlet pi star state. Well, she says, oh, I know how to get that because I get the triplet pi star and then I just make it orthogonal to the triplet to give the right, to make it an orthogonal guy. And yes, it is this one that's the same combination as the tough one of her triplet, but with a minus sign in there. But the thing I'd like you to, and I say, yes, that's the right answer. So all these states that can be made from two electrons in two orbitals, pi squared, pi star squared, pi star triplet, or pi star singlet, they're all listed there. Some of them can be written as a single determinant. As you'll see later in the series of lectures, those kinds of wave functions can be treated using certain kinds of approximations like Hartree-Fock and Muller-Plussett perturbation theory. Other states, triplet with ms equals 0 pi star or singlet pi star, intrinsically have two Slater determinants in them. There's no way that they're equal to just one Slater determinant. So any theory that starts out saying my approximate wave function is one Slater determinant plus some small corrections can't work, at least well, for those kinds of states. Okay, now, I understand this is still getting a little bit tedious, but it's important to go through this. What I want to do next with you is to look at those Slater determinants that I just talked about on this slide here. And everywhere there's an orbital pi, what I'm going to say is pi is 1 over square root of 2, that's just to normalize it, right plus left. What I'm essentially saying here is that think of a pi orbital as a p orbital on the right. I guess that would be your left. A p orbital on the right plus a p orbital on the left. And for pi star, I'm going to say right minus left. So I'm just approximating or writing these pi and pi star orbitals as right plus left, pi, and right minus left, pi star. Why am I doing this? Because I want to now consider how those Slater determinants on this preceding transparency, how these guys, written in terms of pi orbitals and pi star orbitals, how they can be rewritten in terms of left and right. And the reason I want to do that is when you take this olefin and twist it and break the bond, it's natural to think about the electron, is it on the right or is it on the p orbital that's perpendicular on the left? See, I want to talk about how the electron density in those different determinants evolves to become either, I'm going to call it radical or diradical-like, where if there's an electron here and another electron there, that's radical. If two electrons are here and none are here, or two are here and none are here, that's Witter ionic. That's an ionic configuration. And we want to take this olefin and break the bond into the radical situation. That's chemically what happens. So let me show you now the problem. If I ask Diane to take her pi squared, pi alpha, pi beta determinant, and everywhere there's pi, just right plus left, then this Slater determinant, let me not bother with these 1 over square root of 2 factors that are here. They factor out, and they're just numbers, but the part I want to focus on is the left plus right and the left minus right and all that kind of stuff. So here, for the pi, I want to put right plus left. For the pi, I want to put right plus left. So I'll get 4 terms, 4 Slater determinants. See, when I do pi and pi, I'll get right, right, left, left, right, left, and left, right. And it's important to watch the signs. So pi is right plus left, pi is right plus left, so all the signs will be positive. Right, right, left, left, plus right, left, plus left, right. Now, that was just algebra. The problem, though, is that means that this doggone pi squared determinant of Diane's, if I did a calculation with 2 electrons in a pi orbital and I twisted this molecule and broke the bond, that wave function would evolve into a wave function that has 50-50 mixture of ionic and diradical. See these first 2 terms, right, right, and left, left? They are terms that involve 2 electrons here and none here, or 2 here and none here. They're ionic. These 2 terms here, right, left, and left, right, they're the correct diradical things that I want to end up with. So this wave function won't give the right answer. Can't give the right answer when I twist the bond. You say, well, let's look at a couple other examples here. What about the pi star squared? Now in this case, what I'm going to do for pi star is I'm going to write right minus left. So for pi star and pi star, right minus left. So I'll get right, right, minus, minus, left, left. So notice plus, left, left. But then the cross terms will come in negative. So this term also has ionic and diradical terms in it, but not exactly the same mixture. Ionic terms minus diradical terms. The triplet pi star state of Diane's, pi and pi star, if I put in right plus left here and right minus left here, I'll get right, right. Uh-oh, where's that over here? Well, see, the right, right term would give right alpha, right alpha. A Slater determinant that has 2 rows exactly the same will vanish. That is, right alpha times right alpha is 0. That Slater determinant is 0 because the 2 columns or rows in that Slater determinant would be identical. So the only terms that will remain there would be the terms that involve, for example, left alpha, right alpha, and then the term minus right alpha, left alpha. So the triplet pi star determinant is only diradical. So what the heck is going on here? Let me just, on this slide, I'm just going to leave this as a little exercise to you. I've written out the singlet pi star state of Diane's that involve 2 determinants. I've gone through it and expressed it in terms of these lefts and right and so forth, and it ends up being purely ionic. So to summarize this, here's a picture that summarizes it. On the left-hand axis here, I've written sort of the energy, and along the horizontal axis, twist angle. So at no twist angle, that is, the olefin is with the pi, a bond, we have this pi squared determinant. The problem is, as we twist that angle to 90 degrees, the pi squared determinant gave a wave function that was ionic plus diradical. The pi star squared determinant, when we twisted it, it gave a combination that was ionic minus diradical. The triplet pi star determinant, when we looked at it and twisted it, it gave something that was only diradical. And then on that last transparency I went over quickly, the singlet pi star, when we twisted it, gave something that was only ionic. So the deal is, all of these are screwed up. All these things over here give rise to things that are all mixed up. And the answer to this paradox or puzzle, for example, is that to realize that the pi squared and the pi star squared determinants, when you broke them apart, one of them gave ionic plus diradical, the other gave ionic minus diradical. So the correct way that you're going to have to describe the evolution of this pi squared state to breaking apart into just diradical is you're going to have to mix the Slater determinant pi squared and the Slater determinant pi star squared and allow them to combine in a way that out at 90 degrees they will get plus and minus combinations. And I show this on the next slide here. So we had the pi squared that was ionic plus diradical. The pi star squared, ionic minus diradical. At the 90 degree geometry at least, we have to have some way to combine these 2 determinants so that we can keep just the diradical part or just the ionic part. This is what's called configuration. See, configuration means pi squared or pi star squared or pi star. That's configuration. This is called configuration interaction. So the real wave function and the real energy at 0 degrees will involve maybe 99% pi squared and maybe 1% pi star squared in its real description. But as we break that chemical bond, the real ground state singlet diradical will be a 50-50 mixture of pi squared and pi star squared. That is, we'll have to mix pi squared and pi star squared to get an energy curve that sort of comes and is lower because the ionic and diradical split apart into a low energy diradical and a higher energy ionic thing. So this is an example where, what we have so far here is, in some cases, we can use a single determinant as a reasonable approximation, pi squared, pi star squared, or triplet pi pi star. In some cases, we can't even use a single determinant, singlet pi pi star. In addition to that, though, as a function of geometry, in some cases, even if we start out with a single determinant like pi squared, it doesn't give the right single determinant at the product geometry, at a different geometry. So sometimes we have to let configurations actually mix, electronic configurations combine to give the right situation that we want at the perpendicular geometry, in this case, the ethylene. Okay, so let me just summarize this a little bit. This same kind of thing, anytime you have two orbitals coming together, we did olefin. What I could talk about is a hydrogen molecule with a 1s orbital here and a 1s orbital there, forming a bonding sigma and a sigma star. The same kind of problem that we just went through there with the olefin would arise, except instead of being pi and pi star, we'd have sigma and sigma star. The left plus right wouldn't be p left and p right. It would be 1s left and 1s right. But it'd be the same pathologies would arise. Sometimes single determinants are no good. Sometimes configuration interaction has to be used. We could also be breaking apart an ethane molecule into two methyl radicals. We could be talking about the carbon-carbon sigma bond formed from an orbital here and an orbital there, left and right, and the same kind of analysis would be obtained there. So this always happens when you break a single bond, is that you have this problem that the idea that you have two electrons in the bonding orbital and that's all there is to it fails, because when you break that bond, that picture of reality, two electrons in the bonding orbital, breaks apart into a mixture of ionic and diradical character, and you can't have that. You always have to have bonding squared and anti-bonding squared mixed together to give the right breakage at the twisting, or in this case, the stretching of the chemical bonds. Now, the last little topic I wanted to just touch on briefly here is sometimes people say, well, isn't it possible, Jack, that what you could do is to take a Slater determinant that is phi alpha, phi prime beta. That is, instead of being pi alpha, pi beta, couldn't we let it be pi alpha, pi prime beta, and let the pi prime and pi orbitals be the same if they wanted to, like they want to here, but let them break apart, when they break apart into different things, let them become, for example, left and right instead of being pi or pi star. Well, you can do that. The problem, though, is that what you're asking is this, for example, pi alpha, pi prime beta, you want it to evolve to become left alpha and right beta, for example, is what you're saying there, or right alpha and left beta. Either one of those is okay. So what you're saying is let one orbital become right and let the other orbital smoothly evolve into left. Let them start out as being left plus right, but let them change into being purely right and purely left. The problem with that is that Slater determinant, right alpha, left beta, that single determinant is not a singlet. And I think I've written that out over here. So for example, phi alpha, think of it as right alpha, and phi prime, think of it as left beta. So phi alpha, phi prime beta is neither a singlet or triplet. It's a mixture. That is, that Slater determinant I could write instead as phi alpha, phi prime beta, minus phi beta, phi prime alpha, plus phi alpha, phi prime beta, plus phi beta, phi prime alpha. The reason I write it this way is this first combination of two terms you can see is just a singlet couple. See, it's phi, phi prime. It's a singlet. The last term over here is a triplet. So the problem is any function that's like right alpha, left beta, there's something alpha and a different orbital beta, is really a combination of singlet and triplet. It's triplet ms equals 0, and it's singlet, but it's still a combination. So the bottom line is that things like that, letting something be right alpha, left beta, that makes sense, but it's still not the right answer. So when you do a calculation like this, and this is what gives rise to what we call unrestricted Hartree-Fock. See, when we do Hartree-Fock that you'll learn about later, the pi alpha, pi beta, you're restricting both electrons, alpha and beta, to be in the same orbital, pi. That restricted Hartree-Fock is bad, partially ionic and partially covalent when you break the thing apart. This thing here, where you would say, let's let the orbitals pi and pi prime be different, that's called unrestricted Hartree-Fock. You don't insist that the two electrons be in exactly the same orbital. The problem with it is it doesn't give a pure singlet. It gives something that's a mixture of singlet and triplet. So like on these potential curves that I show here, here's the bottom line now as to what you get. You do a calculation on, say, the olefin as a function of, say, this twist angle, or of a diatomic molecule as a function of distance, and that's what I graphed up here, say H2 molecule breaking apart, or ethane breaking apart into two methyl radicals. What you find is here's an energy versus, say, bond length. If you do the calculation with the restricted Hartree-Fock, 2 electrons in the sigma orbital, sigma squared, sigma squared, sigma squared, it gives this curve that rises to a very high energy compared to the right energy, which is this lower curve called FCI. That means full configuration interaction. Just treat that right now as the right answer. So that curve dissociates at a much higher dissociation energy. Why? Because it's giving a state that's half ionic and half covalent, or half diradical. It's wrong. If you say, the hell with this, with these two orbitals being the same, let them be different if they want to. Then you get this curve that's the intermediate one. It looks nice and just like the restricted Hartree-Fock curve near the equilibrium bond length. That's because the two orbitals want to be, that is the lowest energy way of arranging the electrons is, yes, put them in the same orbital. So that it looks just like the restricted Hartree-Fock out to some critical bond length here, about 2.2 it looks like. And then right then, all of a sudden, it turns out it's lower energy to let these two orbitals become different. No longer sigma and sigma, but sigma and sigma prime. They're evolving toward left plus right. See, sigma might be left plus right, and sigma prime will be left plus right for a long time. That's restricted. But right here, sigma starts to be, say, 51% left and 49% right, and the other one starts to be 51% right and 49% left. And then as you pull the things further and further apart, one evolves into 99% right, and the other evolves into 99% left. And that's this dashed line in here, unrestricted Hartree-Fock. Now the problem is you say, well, it doesn't look all that bad, except one thing that happens is right where this bifurcation point is, where the point where the decision to let the orbitals become different takes place. And it's not you making that decision. It's the energy minimization process that we'll introduce that says, optimize things to give the lowest energy situation possible. That energy minimization situation gives rise to an energy that does not have a discontinuity. So the energy doesn't change, but the slope does change. So right here, the gradient of the energy with respect to bond length will be something, and then all of a sudden there'll be a discontinuity in it. And that's really bad if you're doing molecular dynamics calculations, because slopes of the energy, dE, d geometry, is a force. And if you have jerks in your forces, that gives rise to bad behavior. Okay, so just to summarize this, unrestricted Hartree-Fock would give rise to this curve that's just like UHF, but then would deviate from it with a jerk in the slope, and then would dissociate. Now here I've shown it dissociating into something that's not unreasonable, but I've emphasized to you up here that this unrestricted Hartree-Fock thing is a mixture of triplet and singlet, so why is it still not having a bad energy out there? Because when you break these two fragments apart, and they're very, very far apart, the fact of whether this is alpha, alpha, or alpha, beta, or beta, alpha, or beta, beta, doesn't make much difference. That is, when the fragments are far apart, whether they're singlet or triplet coupled is essentially irrelevant. As they're breaking apart, though, it is relevant. So this UHF curve is not quantitatively good, but at least it doesn't dissociate ridiculously as the restricted Hartree-Fock curve does. So that's the end of session number 1. I hope you enjoyed it. Let's go on to the next sessions now.